Alright, let's get started. We're now going to talk about the transform section method for solving non-homogeneous beams. Okay, basically when we say transform section method, we are transforming the non-homogeneous beam into 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 a homogeneous section. So let's say we have here this non-homogeneous section comprising of let's say we have wood and aluminum, and we know that aluminum um, has a modulus of rigidity. Modulus of elasticity of 70. I think this is 70 gigapascals, and for the wood we have 12 gigapascals. Right, here's our original section. Now, when we use the transform section method, we are either transforming, let's say, wood that we will transform the wood into aluminum, or we can transform the aluminum to wood. Okay, so in that way, in that transform section, then we can analyze that transform section the same way how we analyze the homogeneous beams, because technically it becomes homogeneous. Okay, so that's how the transform section method works. Now, for example, let's say I want an all wood. So that means we are going to transform the aluminum to wood. So what that looks like would be something like this. But in order to transform the aluminum to wood, it must have the same capacity. So there's gonna be changes in the geometry, and typically the changes in the geometry would be in terms of the area. So we still have the same depth, and we are just changing the width, because we know that area is simply, the area of this rectangle is just simply the width times the depth right here. So we don't have the same width right here, but the idea is that it must have the same capacity. Okay, so this would be wood, and this aluminum would be wood. Now we can also transform the wood to aluminum. So here's our aluminum, and the wood would be, there's going to be changes in the area, right? So probably something like this. Okay, so this will be, the wood is transformed to, the wood right here is being transformed to this width. Okay, so how do we know that? How do we know the width? All aluminum. Aluminum. Okay, so how do we know how much width there would be? Is through the parameter called the modular ratio, which is just simply the ratio of the modulus of elasticity of the transformed section material to be transformed. Right, so we'll just write A sub t divided by the reference material. So again, this is how I notate this, so that I'll not forget which material is being transformed and which material is my reference. Okay, so right here, just take note that the reference or the base material should be in the denominator, and here this is the material to be transformed. Okay, so let's check this. When we say all wood, um, by the way, this one is the modular ratio. Okay, so as I've said that if here's our depth and here's our width, then this is the original width, right? But this one is larger. That's simply because we need to multiply the modular ratio. And right here, we need to also multiply the modular ratio in this width. Now let's check. Like for example, we know that the reference would be the wood. So this is 12. So right here, n 1 is equal to, so what's the reference material? This is 12, right? 12 gigapascals divided by 70. So we have a numerator greater than the denominator, and that means that we have a greater than 1. Okay, so that's why it has to increase in length. But for this one, so this is 12 divided by 70, so this will be, right, this will be less than 1. Okay, so if it's less than 1, then it has to shorten. Okay, so here's the key parameter for analysis, the modular ratio. Okay, so the next is another equation that we need is the location of the neutral axis. So the location of the neutral axis can be obtained by using this equation. The area times the distance from the neutral axis to the centroid, of that concerned area, plus a sub 2 times the distance y sub 2 is equal to 0. So something like the same as the rec method, except that there was an e right here. Okay, so that's it. That's gonna be our working equation for to find the neutral axis. And again, we can obtain the neutral axis from this variables right here. Okay, and what else? The Fletcher formula. So how do we compute for the stresses? Then, as I've said earlier, that we can analyze this using the procedure or analysis done before. That is just simply sigma sub, let's just say sigma sub r, that's the reference material, that's just mc all over I, or my, let's just use y for now, because c usually corresponds to the outermost fiber from the neutral axis. So this one is the distance, of course, of the reference material, then divided by the moment of inertia, and this moment of inertia is the total moment of inertia of the section. Now for the stress in the transform section, this will be n times this is the modular ratio times the moment, and the distance from the neutral axis would be this one divided by the I total. Okay, so that's just how it works. We just have to transform the section. Alright, so now let's do a sample problem regarding this transform section method. We are going to use the same problem that we solved last time, and we have this problem of non-homogeneous beams. This is wood and this is aluminum, and we have the modulus of elasticity and the dimensions. Then we are asked to find the maximum stresses right here at the bottommost surface or fiber, and then right here at the topmost fiber in the aluminum material. Okay, so but this time we are going to use the transformed section method. Okay, so for the solution, the first step is really to solve. We are going to find the modular ratio, and so that we can transform one material to the other. Okay, so let's write here, solve for n, and choosing aluminum material to be transformed. Okay, in other words, we are going to transform this aluminum into wood. Okay, so in solving that, that's just n is equal to e sub 1 all over e sub 2. And what's the modulus of elasticity of our material 1, the aluminum? This is 70 gigapascals uh, divided by 12 gigapascals, and what we get here is 5.833. Okay, so now that we have that, draw the transform section. Okay, so to draw that, we know that we are going to apply this modular ratio, this 5.83, to the aluminum, to the width of the aluminum, and therefore this will gets longer. Okay, so this is not drawn to scale. Okay, and of course we are going to locate the centroid of this aluminum part, or this transformed aluminum part, and the centroid of this wood, and also the location of the neutral axis. So here's going to be our location of the neutral axis, and therefore from the neutral axis to this centroid, this distance would be y1 bar, and the distance from the neutral axis to this centroid, this is y2 bar. Right, and what else? And we know that this is 50 from this base to the centroid, because this is 100, so 100 to the centroid, that's just 50. And right here, since the thickness is 10, so we know that this is 5 mm. Okay, what else? If this is 50, right, from the bottom, from the bottom portion to the centroid, then the remaining distance, since the total distance is 110, so this will be 60. Okay, and what we need actually is this distance, this C sub 1, right? Because that's for the for the transformed aluminum material, and this one would be C sub 2. Although we are going to express this y sub 1 and y sub 2 in terms of C sub 1 only, because if we use the C sub 2, then we are not getting anything. Okay, so let's write here express. And by the way, we forgot this. This should be, okay, n times 100, because the original width of the aluminum is 100, so n times 100, this is 583.3. Well, this one is 100. Okay, now express y sub 1 bar and y sub 2 bar in terms of C sub 1. Okay, so y1 bar is equal to, so what is y1 bar? This is just equal to C1 minus 5, right? And actually it's just the same as before, and y sub 2 bar is just equal to C1 minus 60. Okay, so now that we have this, applying now, okay, applying, or I think this should be step number 3, this is 4, or solve for the neutral axis. And we know that the equation is a1 y1 plus a2 y2 is equal to 0. So a1, what is a1? What is the area of this? This is just 583.3 times 10. So 583.3 times 10 times this one, which is C1 minus 5, right? Plus the area 2. The area 2 is 100 times 100. And the distance, no, not the distance, but rather This equation, y sub 2 is c1 minus 60 is equal to 0. Now we have one equation, one unknown. Therefore, c1 is equal to 39.74 mm, and therefore c2 is equal to this is 110 minus c1, so this is just 70.26 mm. Okay, and we can also solve for for y1 bar. Okay, so y1 bar, therefore y1 bar is equal to 34.74, and y2 bar is, since this is below the neutral axis, then we have to include the negative sign, so this is negative 20.26. Okay, now that we have that, the next step is to solve for the moment of inertia, or total moment of inertia of what? Of the transformed section. Okay, so I sub t is equal to I sub 1 plus I sub 2, and we know that this I sub 1, we use the parallel axis theorem because we are going to rotate this area, not along the centroid, or not along its centroid, but rather right here, the neutral axis. So let's skip this because you already know this one, and I'll just give you the value, which is 7.088 times 10 to the 6 mm to the fourth, and I sub 2, again you just use the parallel axis theorem. This one is 12.438 times 10 to the 6 mm to the fourth, and therefore I total is equal to, if you add this is just 19.526 times 10 to the 6 mm to the fourth. Okay, so that's our moment of inertia. So now we can solve for the flexural stresses, because if you recall that the flexural stresses is just mc all over I, or my all over I. We have this, we have that, and we have this moment, so we can solve now. Okay, so for aluminum, it's just sigma 1, or let's just say sigma 1, right, is equal to, we need to multiply this to, because this is the material that we transform, so we need to multiply the modular ratio n to the flexure formula. This is mc sub 1 all over I total. Okay, so this is 5.83. Okay, and this one is 3. However, the given unit is 3 kilonewton meter, and we are working, I think we'll work with Newton mm, so that we can get the megapascals unit. So 3 times 10 to the 6, so that right here you get a Newton mm. Okay, times the distance, so c sub 1, I think this is 39.724 mm. Okay, divided by the I total. The I total is 19.5, let's say 19.53 times 10 to the 6, and this is mm to the fourth. So our unit would be Newton mm, Newton over mm squared. this will be 35.6 megapascals. And by the way, this is negative because this is compression. Okay, and the next is oh sorry, for 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 wood. Okay, for wood, um, this, let's say this sigma 2 is equal, since it's the reference, then we don't need to multiply, or we are not going to multiply the modular ratio. This is 3 times 10 to the 6 times the distance, this distance to no, sorry, from the centroid of the transform section to this one. Okay, so that's C sub 2. Well, C sub 2 is 70.26. So divide that by the total moment of inertia, 19.53 times 10 to the 6. And what you get here is 10.8 megapascal. So which is just the same as the rec method. Okay, and finally, we should. It's also a. It's also. It's also good to provide a summary or something like a sketch. This is a sketch of the section. So if this is the aluminum, and this is the wood, and right here is our neutral axis, then what's going to be the stress distribution? Okay, so for aluminum we have 35. So that means it's something like this, but for wood it's only 10. So let's say somewhere here. Okay, and going this way, actually 10 would be here. So right here, maybe it's not 10, I'm not sure, but the value of sigma 2 is 10.8, and it's right here. Okay, so that's our stress distribution, 35.6 megapascals. Okay, so I think that's enough, but it's also possible to have a composite beam that looks like this. Okay, so instead of having this having it this way, right? It's also possible to have a section that looks like this. So right here we have a brass material, and brass material on both ends, and we have steel in the middle. Okay, so if this is the problem, then the centroid, I mean, we don't have problem looking for the neutral axis because it's just gonna be right at the middle. Okay, and it will be 1.5 inches. Okay, so now let's try to solve this problem. And by the way, this problem is taken from the textbook by Beer et al. And this is example 4.03, and the page is 232. A bar obtained by bonding together pieces of steel and brass as the cross section as shown. Determine the maximum stress in the steel and in the brass when the bar is in pure bending with bending moment of 40 kip/inch. Okay, and we have here the modulus of elasticity, and I think we can dive right away to the computations. So first, solve for the modular ratio using, okay, so let's choose the brass as the reference material. Okay, so N is equal to ES all over B, E sub B. Okay, so ES still is greater or stronger than the brass. This is 29 divided by 15. What you get is 1.933. Okay, so once we have the modular ratio, then we should draw the transform section. Okay, so here's our transform section. We are going to transform the steel, right? We are going to transform the steel. So instead of having 0.75, it will be something larger because our modular ratio is 1.9. Okay, and the centroid is just right here at the midpoint. So this is 1.5. Right, this is 1.5 as well. And right here, this is 0.4 inches. This one is 0.4 inches. And this one, this width right here, this is n times 0.75 inches. So this is equal to 1.45 inches. Okay, so here's the length. And the total, 1.45 plus zero point 0.4 plus zero point 0.4, the total is 2.25 inches. Okay, so again, we multiply this modular ratio to the width of the steel. Okay, the next step is to solve for the moment of inertia. And by the way, since this is transformed, then this means that this is steel. Oh, sorry, this is brass because our reference material is brass. These are all brass. Okay, so for the moment of inertia, total moment of inertia is just simply 1 over 12 base times height cube, and the height is this, and this is our base, it's 2.25. We don't need to use the parallel axis theorem simply because we are rotating this area along its centroid. So this is 5.063 inch to the fourth. So now that we have this, and we know this one, actually this is C1. By the way, this is C sub 1 from the neutral axis to the topmost fiber and from the neutral axis to the bottommost fiber. Then we can solve, actually they have the same units except for the sign, but let's solve for the value. Solving now for the flexural stress. So for the brass, okay, for the brass we have MC all over I, and so M, we have the same M, the distance, this is 1.5, and I total, we have here 5.063. So let's write it here, 40 kips inch times 1.5 inch divided by 5.063. I think this is inch to the fourth. So our unit would be 11. The value is 11.85, and the unit is in KSI because this is in kips. And for steel, we just have to multiply the modular ratio n times n, and let's consider this. Actually, they are the same because they're just simply the same. Okay, so let's just write that, and MCO over I total. And in this way, actually, it's just the same thing because, I mean, it's just the same value, 11.85. Right here, this is 11.85. And we just have to multiply that to the modular ratio. Okay, so what we get is something like 1.933 times 11.85, and this is 22.9 KSI. Okay, so that's it. Okay, so in the next video, we'll be moving on to the shear stresses in beams. So see you in the next video.